Okay, so today we're going to discuss the quantum mechanical postulates, and that's going to get into the building of the wave function and some of the properties of the wave function. So there are some extra notes that I added this morning that are from the chapter 3 of the textbook. And so I went ahead and merged those in here, and then I've re-uploaded the handout. Don't be upset about that. It's just extra content. It's not, it's not like, I would say just don't get too upset about that. I just thought this morning I want to add those beautiful wave function pictures that I put in that chapter. You have all that information. And so there's a new set of notes this morning, but it only has like 6 new slides in it. Okay, so it won't change what we do this morning at all. But I really thought it was a nice progression of building up that wave function, and I hope you agree. So let's jump into it. First of all, these are the quantum mechanical postulates, and we're not mathematicians, we're chemists. So what do we even mean by a postulate or an axiom? Okay, so you could say I postulate something, and that's to suggest or assume the existence of, but notice it's an assumption. You're assuming that this exists as a basis of reasoning, okay? And then also it's a noun, a thing suggested or assumed to be true as the basis for reasoning. Notice that these are assumed to be true. They're not proved. So your postulates are your starting points. And that's a big deal in science, especially philosophy of science. You know, what are the starting points for your reasoning? And so these are the starting points for the reasoning of quantum mechanics. So everything has a basic set of assumptions. And so these are the basic set of assumptions that quantum mechanics is based on. A lot of times when you're confused by quantum mechanics, it's because you don't understand one of the postulates. And you don't know why you would believe that. Well, the thing is, it's just, that's the starting point. It's okay to struggle with that because it hasn't been proved. These are assumed to be true. They're not proved, they're assumed to be true. Now, we have confidence in them because they match the data so well, but that's not a proof of it. That just shows that they're useful. Usefulness doesn't necessarily mean true. Okay, so this is the tension that we have in quantum mechanics. So in mathematics, it's an assumption used as a basis of mathematical reasoning, and this lecture covers those postulates that are the bases for quantum mechanics, and basically the math of wave functions. So postulate number 1, the state of a quantum mechanical system is completely specified by the wave function. So all quantum systems are described by wave functions, even if they're particles like atoms. Okay, we can see atoms with the tapping needle of an atomic force microscope, but we can also describe that particle with a wave function. Okay. We can have experiments where light behaves like a particle, but we can describe that light as a wave function. Here's part of that same postulate. The square modulus of the wave function is the probability distribution of the particle described by the wave function. No, it's not just the square, but it's the square modulus, and this little star is an important piece if you have a complex wave function, something with the imaginary eye. So the probability that a particle will be found at time t in a spatial interval centered on x0 will be given by the square of the wave function. And so if you integrate over all space, then the probability of finding that particle in all space is 1. So that's a defining characteristic of the wave functions. If your wave function isn't normalized, and that's what this is talking about, meaning you integrate over all space and that integral equals 1, then you've got an incorrect wave function and you need to correct it. All space, in terms of our 4-dimensional space, x, y, z, and t, this would be a quadruple integral. Okay, very, very complex. And so in this course, we're just dealing with things in 1 dimension. So our particular integral will be on the x-axis, and it'll be in a box, so it'll have limits. So we're going to go from one side of the box to the other. That's all space for us. But for a hydrogen atom, it'll be from the origin of the nucleus all the way out to infinity. Okay. And so you would have to have a wave function that goes to 0 at infinity. And you could stop integrating when this probability gets to be, say, 99%. Okay, that'll be just in a few angstroms. To go out to actually 1, you'd have to integrate all the way out to infinity. Now, you might have an analytical solution to that and know what this integral sum converges to as x goes to infinity, and that would be fine. And so this is our case, minus infinity to positive infinity of a 1-dimensional wave function is set equal to 1, and then we modify the wave function to force this to be true. We'll do that today for sure. So here are invalid wave functions. For this integral to work, your wave function can't have breaks in it. And so this is an invalid wave function because it's not continuous. There's a break here. Now, we'll see later that to calculate the energy of a wave function, you need to do the second derivative. And so if I'm looking at this first derivative and I look here, coming this way, the slope is negative. And then if I'm coming this direction, the slope is positive. What is the slope at that broken point? It's double valued. And so I have to have a continuous first derivative too. Otherwise, I can't take the second derivative. Okay? So it can't have any kinks in it. All right, it's got to be a smooth function. And then single valued. So this wave function is not single valued. So at this particular value, it's got 3 results. Okay, so what's the slope at that point? Well, it's positive here, it's negative here, and it's positive there. So I can't do the derivative of that function. It's not single valued. If the wave function, if I square that wave function and integrate over all space, and that's supposed to equal 1, then my wave function can't go to infinity, right? Because I can never get infinity to equal 1. Okay, so these are 4 ways that your wave function can break. Okay, and so wave functions for electrons, nuclei, molecules have been developed. They must be continuous, have a continuous first derivative, must be single valued, and must be finite. And so let's build a wave function for a particle in a box. So this is one of the new slides. So let's say our box length is 7 angstroms, okay? And we're just going to pick sine because it's got, it's an oscillating function. And so we plot sine on here from 0 to 7. And notice that it is finite between 0 and L. It doesn't go to infinity anywhere. It's continuous. It has a continuous first derivative. There's no sharp kinks in it. But it's not 0 at the boundary. That wasn't one of our four rules, but it's still a good rule, right? If I'm going to set up a standing wave between my boundaries, I need to have a node at the boundary. So I really need it to go to 0 at the boundary, okay? Or it needs to meet up with its counterpart on the other end. Okay, so let's figure out how we can get this to be 0 at the boundary. Notice this is x, and what if I were to multiply this by pi? So I would have x be a portion of pi, but I would like the pi to be scaled by L. So it's kind of like I want to convert x from angstrom units in angstroms to radians. And so I want to multiply it by pi radians over L angstroms. You see how that's kind of like a conversion factor? I'm converting the units from angstroms to radians. And pi will get me 1 lobe of this sine function. I could do 2 pi as well, but we'll just do pi. And then that'll pin that other end. It'll move this piece over here by multiplying by pi over L. So let's do that and see what we end up with. So here's our x times pi over L wave function, and now it's pinned at 0 on both ends. Okay, so now it's 0 at the boundaries, but it's not centered on 0. I would like to have my wave function centered on 0 just so that later when we deal with symmetry, we can see if it's symmetric on the positive and negative x-axis. And so I'm going to slide this thing over. How do I get it to slide over? I don't want 0 to be pi x over L. I actually want it to be pi over 2. I want this to be 0. And so I could add pi over 2 inside here. And if I add pi over 2 inside here, then when x is 0, I add in a pi over 2 and it actually moves 0 over here. So I'll show you that. This is the next one. So I add a pi over 2 to slide 0 over to the middle of that wave function. And now when x is negative 1/2 of L, I end up with pi over 2. Okay. And when x is positive L over 2, then I end up with this positive half of the box. Okay. And so now my wave function is centered on 0, but it doesn't have any quantum numbers. This is supposed to be a quantized equation, and it's supposed to go up in curvature with quantum numbers. And so if you add a function like a constant in here, you're going to create a higher frequency. And so let's just put our quantum numbers inside here. Let's pick n as our quantum number. And so now we have our quantum numbers, right? I put an n in both of these. And so now when n equals 2, I go to 2 pi. When n equals 3, I go to 3 pi, and so on. And so I have my quantum numbers, n equals 1, n equals 2, n equals 3. As I go up in quantum number, I have more oscillations. That's more curvature, and that's going to be a higher energy. So this is going to be great when we work out the Hamiltonian and we calculate the energy. So now my wave function has quantum numbers. But notice that they all go up to 1, right? So the maximum is 1 here and minus 1 on the minimum. And so if the wave function ever equals 1 at any point, then the square of that wave function and the integral over all space can't equal 1, because just this value equals 1. And so it's going to be way more than 1 when I integrate this wave function squared. So now we need to normalize the wave function. And this is where we get back into the notes that you have. Okay, but wasn't that nice? Nice little side trip. How do we build a wave function? Okay. So let's talk about orthonormality. Our wave functions have to be normalized. So when they square them, they've got to sum to 1. Orthogonality also means that the wave function for quantum state 3 is not just the sum of wave function 1 plus wave function 2. It's another way to say each state has to have its own wave function and not be a combination of other wave functions. Okay. And so whenever we're looking at wave functions times each other, and so I'm going to go ahead and put an n on this guy and an n prime here. Okay, so if these two quantum numbers match, and I essentially it's a squaring of that wave function, integrate over all space, it equals 1. But what I need for orthogonality is if these n's are different, then I need that sum to be 0. Now, we get lucky with sines and cosines and e to the x because those produce orthonormal sets. So if you change the quantum number and if you take n equals 1 wave function and times n equals 2 wave function and integrate over all space, the sum equals 0. And we can see this. I've done this in Excel, and I've calculated the integral of all combinations of wave functions, at least for the first 5 quantum states. And you can see that when I've got quantum number 1 wave function times quantum number 1 wave function and integrate over all space, I get 1. But if I take 1 times the wave function with quantum number 2, I get 0. And if I take 1 times quantum number 3 wave function, I get 0. So do you see, anytime it's off that diagonal, the sum is 0. And if it's on the diagonal, like here I have 4 times itself, okay, that's just showing that quantum state 4 is normalized. Okay, so this Kronecker delta, I can't believe he got his name over a function that just says 1 if n equals n and 0 if n doesn't equal n. But hey, that's great. I want to get my name on something. I don't know what I can invent, but still, Kronecker delta is very simple. It has 2 results. When the n's match, then it's equal to 1. When the n's don't match, it's equal to 0. And what do these angle brackets mean? It's a little review from last time. Integral, yeah. So the integral of wave function n prime times wave function n integrated over all space is equal to the Kronecker delta. So this orthonormality right here is this one statement. And so now you're really thinking or writing math like a quantum physicist. Okay. So let's actually do the math. Normalization of the 1D particle in a box. So we have that sine n pi x over L plus n pi over 2, but it's not normalized. So we're going to figure out what this constant would be in front to make this integral equal 1. And so we put this n in here as a placeholder for the normalization constant, and we're going to solve for n. We set it equal to 1 because that's the definition of normalization, and we integrate over all space, which in our case is minus L over 2 to L over 2. So we're just going from the left to the right of the box. We're squaring that wave function. We have this variable n. We can pull n out since it's a constant. So we pull it out, it's n squared over here. And then we have the same arguments inside. And that's the only time you can say it's sine squared, is we have n pi x over L plus n pi over 2 in both of the arguments. And so we can say that that's sine squared. It's the same thing. Okay. So we have sine squared. We can do a trigonometric substitution to reduce that power. So we don't want to try to integrate sine squared. We want to get it down to something we know, like sine or cosine. So we can take that sine squared and we can use that half angle relationship. And then we end up with two integrals. The integral of 1/2 minus the integral of 1/2 times cosine and all this other stuff. Notice it's 2u inside. And u is all of those arguments inside. Okay, so we have a 2, and then here the 2's cancel. So this 2 is gone. That's why we just have n pi here. And we have a 2 n pi x over L. Everybody follow the calculus so far? Okay. So we can rewrite that as two integrals. The first one is super easy. The integral of dx is x. Okay. All right. What's the second one? Okay. So the derivative of sine is cosine. Okay. So the integral of cosine is sine. Okay. And so we don't lose the negative sign there. So the integral of cosine is sine. And we've got to take the inverse of everything inside that is a function of x. Okay, so that's where this L comes from, and that's where the 2 pi comes from, but it ends up being 4 because we already have a 2 here. So it was this 2 and that 2 combined to give us the 4. Okay. And then we evaluate that at L over 2 and subtract the evaluation at minus L over 2. And we do that for the x integral and for the sine integral. So let's put all that stuff in. So this first one is right here. And so positive L over 2, and then we subtract the evaluation with negative L over 2. So this piece is one integral result, and this is the other. So then we put L over 2 in for x, and then we subtract, which means we change the sign, so now it's a positive, and we put the minus L over 2 here. Okay, so our 2's cancel, our L's cancel. We have a minus n pi and a positive n pi, and so those all cancel. It's going to be the sign of 0. This L is gone, that's gone, the 2's are gone. We have an n pi plus an n pi, so we end up with 2 pi times n. So let's go ahead and evaluate that. So notice we've got the sine of 2 pi times n and the sine of 0. Well, you know the sine of 0, right? It's 0. And think about the sine function. So the sine function looks like this. So this is 0, this is pi, this is 2 pi. What if it keeps going? It crosses again at 3 pi. It goes under, crosses again at 4 pi. So this is one of the most useful things to have in your head. Integer multiples of pi are all 0 for sines. And that's going to be really useful in this week's lab. So when you're doing the results and you get a bunch of sines and you can figure out, oh, this just is integer multiples of pi, all of those sine terms are 0. So this one is 0 and this one is 0. So the only thing that survives are these n squareds, L's, and 4's. So we end up with this integral result. Remember, we set it equal to set it equal to 1. So this integral result is set equal to 1, and we solve for n squared. So n squared is the square root of 2 over L. Okay. So now we have normalized wave functions. This is back to a new slide, but just showing you that piece in front is the normalization factor. And notice now our wave functions don't go all the way up to 1. They're something less than 1. If I were to square every one of these and integrate from left to right, the result would be 1. So here's another new slide. It's just showing you the particle in a box, because that's the system we're using. That electron is stuck on this wire, and at the boundaries, the potential energy goes to infinity. So that's a way we ensure that it stays in the box. And I've offset the wave functions by the energy. We haven't solved for the energy yet. We'll do that soon. But these are the first three quantum states for the particle in a box for a length of 7 angstroms. This is the energy for an electron. And I've increased their factor by 200. So I've multiplied the results by 200 so you could see them. Wouldn't be very impressive if they're just really tiny. And so I went ahead and scaled them up for just for aesthetics. Now, thinking about this integral over all space equal 1, right? We're looking in the whole box for the particle. What if we just looked at the first 10% of the box? What do you think the result would be? Should be 10%, right? If it was a classical particle, like if we had a small particle in this room and it had the freedom to move anywhere in the room, and we tested 10% of the room to see when that particle was, and we looked for a long time, let's say, we would expect an equal probability of being anywhere in a room. And so we would expect 10% of the time that particle would be found in 10% of the room. Same thing here. But quantum mechanics is strange. So this is one of the strange features of quantum mechanics. Notice that dashed line on the first 10% of the box. If we integrate over all space, it equals 1. So these are the squares of the wave functions. But if we just integrate the first 10%, what do we get? Notice there's very little probability that the ground state particle is going to be in the first 10% of that box. Okay. In fact, it comes out at like, let's see, if this is 0.01, 9, 8, 7, 6, 5, 4, 3, yeah. So it's less than a 1% chance that it'll be in the first 10% of the box. That's weird, isn't it? The electron could be anywhere on that wire, but it's only got a 1% chance that it'll be in the first 10% of that box. It's not going to be near the walls. And that's a quantum behavior. That's bizarre. Notice if I increase to quantum state 2, now it's a 2.5% chance that it'll be in the first 10% of the box. If I go to n equals 3, okay, now I'm at 10, 20, 30, 40, 50, 5% chance it'll be in the first 10% of the box. Okay. And this is a funny behavior that you see with quantum mechanics and the wave nature of light. Okay. Look at the x-axis, what I'm plotting, quantum number. And so if you go along and you continue to just integrate the first 10% of the box, it looks like it reaches its classical value at n equals 1, 2, 3, 4, 5, at n equals 5. But it's not really. It's just coincidental, okay? That one has 5 lobes, and one of the lobes is right there, and you're getting half of that lobe. So you're getting 10% of the wave function. And notice at n equals 6, it goes above that. So at n equals 6, there's more than a 10% chance it'll be in the first 10% of the box. Look at this funny business, how it oscillates up and down, but notice how it dampens out. When I get to n equals 50, it's almost behaving like a classical particle, that it would be equally distributed across the whole box. And if I'm looking at the first 10% part of the box, I would have a 10% chance that the particle would be there. And this is a principle I want you to take home with you. As the quantum numbers go up, the quantum behavior disappears. As the quantum numbers go up, the quantum behavior disappears. So there's a smooth transition from quantum funniness to classical physics. So there's no dividing line between the quantum realm and our big realm. Okay? There's not some magical place where you cross a line and now you're in the quantum realm. It's a smooth transition. You will not hear that in popular press. People write books and the quantum enigma and all this, and I call it witch doctorism. Okay? They put a bunch of crazy sounding physics out there and make you think that they understand the world way better than you could ever understand it. And therefore, when they speak on something that's totally unrelated to physics or physical chemistry, you should trust them with that too. Right? That's witch doctorism, and I hate it. That's why I'm taking a few minutes here to tell you there's nothing magical about the quantum realm. It's bizarre, no doubt. Okay, but beware the witch doctors. Okay, we're going to talk about the funniness of quantum mechanics, and therefore you should trust them about all of reality. No. Okay. Yes, quantum mechanics behaves really strangely in the lower states, but as you get higher in quantum number, then that strangeness starts to taper off, and you see exactly what you would expect. If you've got an electron in a box, and it could be anywhere in the box, 10% of the time it should be in the first 10% of the box. If it's a high enough quantum number, yeah, absolutely. If you get down to the ground state, maybe not. Okay, so then orthogonality. Let's just prove that calculus-wise. So let's take the sine functions with different quantum numbers. So now we're going to keep n and n prime separate. Notice carefully here. So n is not equal to n prime. So we're going to keep this n here and this n prime there. So we can't do a sine squared because it's not the same stuff in the middle. All right, we'll pull that square root of 2 over L out, and there's 2 of them, so the square root goes away. And so now we need to do this substitution. Instead of having sine times sine, we can do this sum of cosines. And so we have it's like if you have cosine. If you have sine of v times sine of u, then you end up with the cosine of v minus u and the cosine of v plus u. And so that's what we're doing here. Okay, I should have written the substitution out somewhere. And so now we have the integral of 2 cosines. That's going to be great. Pretty straightforward. We can distribute that integral and distribute the 1 over L. Where'd the 2 go? Well, it was the 1/2 of these cosines, and so the 1/2 canceled the 2. All right, and so we've simplified the internal arguments. We have the n prime pi over x, and I've got a regular n, so I go ahead and combine those x terms and combine the constant terms. Same thing over here. Okay. And so the integral of cosine is sine, and we bring out the inverse of what's inside the arguments. Notice the L comes out on top and cancels with this L. So when it comes out, the L's are gone. And we just have this inverse of the pieces that are a function of the x. So we don't have these constants. These things go away. Okay, and we have them inside the sign, but we don't have them coming out front. And then we evaluate that integral at L over 2 and subtract the evaluation at minus L over 2. And so those go in for this x here. The L's cancel. And so we end up again with integer multiples of pi. Now, how do I know that this is an integer multiple of pi? Because my quantum numbers are integers, okay? And they're different. So I'm going to end up with some integer multiple of pi here, and I also have a sign of 0. And so this is 0 and 0. So again, no matter what my quantum number is, I did numerically up through n equals 5, but what about 6? Right, numerically, I couldn't say anything about quantum state 6 because I didn't calculate it. Or 7, or 8, or 50, or 100. But when you solve the problem analytically, you know it applies to all n primes. So now I absolutely know, beyond a shadow of a doubt, that no matter what n's I pick, as long as my quantum numbers are integers, if they're different, the result is going to be 0. So I've proven that orthogonality case for our wave function. So our wave functions are orthogonal to each other, and they're normalized. So that's beautiful. That's what we have to have. Let's look at postulate 2. So that was all just postulate 1. It all came out of that orthonormality condition. The others are not that involved. Postulate 2 deals with observables. Every measurable property, there's a corresponding operator in quantum mechanics. So an experiment in the laboratory, like a spectroscopic measurement, is simulated in the theory by operating on the wave function. And so here are the operators. Here's an operator for momentum, right? In classical physics, momentum is just, the mass times the velocity. In quantum mechanics, you operate on the wave function, and that'll give you the momentum. The kinetic energy, this is part of the Hamiltonian. So this piece right here is a part of the total energy operator. And again, the Hamiltonian is the total energy, so you have to add in the potential energy. So you have the potential energy piece and the total energy piece. Conveniently for us, our particle in a box, the potential energy inside the box is 0. So that's nice. We could have used a harmonic oscillator and put in like a Hooke's law minus kx squared, and you get a parabola. Okay, and so then we would have a potential energy piece here that would be that potential energy function. In a hydrogen atom, you've got a negative electron and you got the positive proton, and so you have Coulombic attraction, and so that's the two charges of the particles divided by r, the distance between the particles, and so you could calculate the potential of the electron and its distance from the nucleus. So potential energy doesn't have to be 0, it just is 0 in our particle in a box situation. And then the position operator is x, so you would just multiply x times your wave function. A lot of these equations, when you're doing the observation simulation, you end up with an eigenvalue equation. And so the measurement of an observable value, whether it be energy, position, momentum, will yield an eigenvalue of the corresponding operator. So eigen is just German for same. You're going to learn a little German here. I'll put it in quotes so you know that that's what I'm talking about, same. And so eigenvalue and eigenvectors, you'll see where the word same comes in a second, okay? The properties of the wave function and the operator will cause the system to be quantized. Notice that it was our wave function interacting with the boundary conditions that gave our quantized system. We needed standing waves, things that could go up by harmonics and have still be pinned to 0 at the ends. It was that boundary condition that caused our wave function to have certain properties inside the argument, like the length of the box and pi and so on. So when we were trying to meet our boundary conditions, that's when we added in pi over L. That's when we added in that n pi over 2. So it was this properties of the system and the wave function working together that created our quantized system. And these eigenvalues are the quantized observables. So we'll do the energy one in this morning's class. Okay, so let's solve for the energy equation, and this is an eigenvalue equation. And notice how this wave function here is the same as that wave function there. So that's the same part, right? Same. You're looking back at your notes, you're not going to understand what that means, but they're the same thing, okay? And so we operate on this wave function, and we get the same wave function back. That's the eigen part of the eigenvalue, okay? And the piece in front is the eigenvalue. That's the value part. So let's see how this works. So we have the Hamiltonian operator. We don't have any potential energy, but we have the kinetic energy piece. And you notice that that's why it's called an operator. Operators do something. It's not just like you're multiplying by a constant, right? Like if you're doubling it, you're just multiplying by 2. It doesn't really do anything. But the second derivative, you're doing something. You're taking the derivative of that curve. So you're operating on that curve. And then that's going to equal the energies times our wave function. So we're going to leave the right side of the equation alone, and we're just going to operate on the left side. So let's take the first derivative of sine. Okay, derivative of sine, if you wanted to draw the sine out, here we've got sine, it starts out like that. The slope of that curve is 1. Well, if we're at 0, which function has a value of 1? Positive cosine or negative cosine? Positive cosine. So just try to, if you can't remember that, just think, okay, the derivative is the slope. I draw the sine function. I know the slope of the sine function at point 0 is positive 1. Therefore, I know the derivative of sine is cosine, because cosine starts at positive 1 when you're at 0. So there we go. We have the derivative of sine is cosine. We don't change the minus sign because it's not negative cosine. So we leave that alone. And then we pull out the arguments in front of x. So we end up with n pi over L. So they're outside now. Okay. We've gotten rid of we're taking the first derivative. So now we've got another derivative to do to make it the second derivative. So we take the derivative of cosine. And we could do the same thing for cosine. If you can't remember, here we are at 0. Okay. And cosine starts up here at 1, and it goes down like that. Okay, so the slope at 0 for cosine is the slope is 0. Okay, and that doesn't really help us with sine because sine goes through 0 at 0, but it goes through with a positive slope, and here the slope of cosine is getting more negative. Okay. So the derivative of cosine should be minus sine. It should be the opposite behavior of sine. And so notice we have a negative sign here in front of cosine. If I make minus sine, then that negative sign is canceled out. Okay. And so that's where that sign goes. And then we pull out another unit of the n pi over L. So now we have n pi over L squared. And guess what? We got our same function back. That's cool. We did the second derivative, and we got the square root of 2 over L times sine and all that stuff in the middle. And so that means, by inspection, that the energy is equal to all this stuff out front. So we've solved for the energy. We've solved Schrodinger's equation. That's pretty cool. Okay, let's clean that up. This h bar, we didn't really talk about that. H bar is equal to h over 2 pi. Again, the lazy chemists making up new things just to avoid writing over 2 pi. Okay, so we're going to clean that up. So this h bar squared means there's going to be a 4 pi squared in the denominator, and we got a pi squared here. So the pi's are gone. That's where they went. We lost the bar on the h, and that's where the pi's went. But we ended up with a 4 from the h bar squared and a 2 here, so that's where the 8 came from. Okay, and then we still have n squared, we have L squared, and we have the mass of the particle. So there's our energies. That's the particle in a 1D box energy equation. 1D PB. You will see that abbreviation a lot. The 1D particle in a box, 1D PB. Okay. Now, expectation values, this would be the same kind of thing we just solved, only it's an integral form of the Schrodinger equation. If a value of an observable is measured once on many identical prepared systems, the average value is known as the expectation value. Okay. And so this is the full, written out for a generic operator A. Okay, we have A sandwiched in between the wave function and its complex conjugate, integrated over all space, divided by the wave function times its complex conjugate, which again, this piece right here should equal 1. Equals 1 in a normalized system. Okay. And so for the energies, our expectation value for quantum state 1, if we did this equation, we would get energy 1. If we did it for 2, we'd get energy 2. If we did it for quantum state 3, we'd get energy 3, and so on. So this gives us our energies for our different quantum states. If we did this for n and n, we'd get the general equation. So it's essentially saying that if I take Schrodinger's equation, H psi equals E psi, and then I left multiply those by the complex conjugate and integrate over all space, and I integrate over all space, okay? This E is a constant, right? And it can come out front. So I'm going to do that next. And then I can just divide both sides by this integral, and I end up with, so I'm going to take this piece right here and move it over there. E is equal to the integral there. So that's the expectation value for the energies. You could do the same thing with all of the other observables, momentum, etc. So that's where that came from. And then lastly, in spectroscopy, this is the ramifications of the postulates. And so this really isn't part of that postulates chapter in Atkins, but I wanted to go ahead and relate it to spectroscopy. Since spectroscopic transitions occur between states, so we need the energy for state 1 and the energy for state 2, and so that would be this difference. So delta E is equal to E2 minus E1, which this just shows you how the wave functions are involved. And I just really wanted to show you this, that spectroscopy is measuring differences in energy states, and those energy states are where they are because of the wave functions. This tells us that transition energy. And so if we were to do a spectrum, and there'd be a spot right here for delta E, that's where our peak would be in the spectrum. So this wave function is involved in the x-axis and telling us where that peak would show up. We'll see in a couple of lectures what we do for the y-axis in a spectrum as well. Okay? But for now, today, we're just talking about the x-axis in a spectrum. And so this transition energy, frequency, and wavelength equations, this is an important page for you. You notice these little explosions here telling you this is a hint for the homework. Okay, so you can go back through the notes and see those little homework hints. This is a big one. This is one that people always email me about, okay? So pay close attention on this one. We can solve this transition energy equation by taking the general equations for energy and doing a subtraction, okay? So we're going for all transitions from state n to n prime. So it could be 1 to 2 or 1 to 3. It could be 4 to 7. It could be all the differences. And so let's solve this analytically so we get one equation for all the transition types. That's what we mean by the transition equation. And we have these three types. We have the transition energy equation, the transition frequency equation, or the transition wavelength equation, because you have different types of spectra. Maybe your instrument gives you wavelength as the x-axis. Maybe your other instrument gives you wave numbers or something like that. Okay. So here's the energy. What I've done is n plus delta n is equal to this n prime, okay? And so everywhere there was an n squared, I put n plus delta n, and now it's really straightforward algebra. It's not even anything that difficult. Notice the h squared and 8ml squared come out front, and we just have a nice little polynomial to solve. Okay. So we're just going to multiply this through and clean things up. Okay, so I've got the n squared, I've got 2 delta n times n, and delta n squared minus n squared. So the minus n squared and the n squared are gone. And so I have this, I went ahead and pulled a delta n out front and left this piece over here, okay? you'll see that that's going to be a familiar type of transition equation that we have in other spectroscopies, like rotational spectroscopy and vibrational spectroscopy. Okay, so this is the energy equation. Remember that energy is equal to h nu. So this is frequency. Okay. And so the frequency equation, so these are all three transition equations. Here's the energy transition equation, here's the frequency transition equation, and then here's the wavelength equation. So what's new? What's new?
Frequency.
Yeah, but what is it? C over lambda. Remember, you're supposed to say that on campus when someone asks you what's new. So what's new? C over lambda. So then I could take this new and equal to C over lambda. And so then I'm going to invert that thing to get to lambda. So that's why now I have the n plus delta n in the denominator here, and everything over here is upside down because I solved for wavelength. So if I have a spectrum, this tells me where my wavelengths are. Lambda 1 to 2, lambda 2 to 3, etc. And so I have a peak here, and a peak here, and so on. And these would all, since this is 1 to 2, that's delta n equals 1. Delta n equals 1. And so we'd have a 1 for all the delta n's, and I'd have an n equals 1 here for the first wavelength. I'd have an n equals 2 here for the second wavelength, and so on. So this is the equation for all of those wavelengths, and that's where my peaks are going to be. So we've pretty much solved the x-axis for the particle in a 1D box. I know right where my transitions are going to be. If I know the mass of my particle, right here, and if I know the length of the box, how I've constrained that electron or proton or whatever, I now know what the x-axis or the horizontal axis of my spectrum is going to be like. It's going to have transitions at these places. I don't yet know if the thermal population will be enough to give me a signal. That's the Boltzmann distribution. And I don't know if the probability of wave function 1 going to wave function 2 is allowed. And that's the transition dipole moment, and we're not there yet. Okay. But we've solved the horizontal axis and the energy equation and the Schrodinger equation. There's a lot in one lecture, but that's why I record the video. Okay, so you can go back and check it out, and then that'll help you this week in the lab. Okay, and the last part is time dependence, which we're not going to deal with. Okay, but you could also look at the time dependence of the wave function.